Hello, everyone. Welcome to my talk on life as we do not know it. In this talk, I would like to present an alternative viewpoint of life and lifelike systems as we do not know it. And what that title really means is I would like to take a different take on life, which is different from carbon-based life that we have grown accustomed to seeing on this planet. In this talk, I will raise more questions than answers. Let me begin by actually with a story. And the story is as follows. Many, many years back, I was working in Boston. I was stuck in a huge amount of snow in 2014, actually, or 2015, almost 9 years back. There was a huge amount of snow in Boston, and I was stuck in that city for almost 2 weeks. The entire city had shut down, and I was just almost like quarantined at home for 2 weeks. And I'd come across this well-thumbed copy of a short story by Arthur C. Clarke. The story is called Crusade, and the science fiction writer Arthur C. Clarke wrote it in the 1950s, in sort of the heydays of science fiction. I would just like to take maybe a minute to narrate a few lines from that story. The story is called The Crusade. It was a world that had never known a sun. For more than 1 billion years, it hovered midway between two galaxies, the prey of their conflicting gravitational poles. In some future age, the balance would be tilted one way or the other and would start to fall across the light centuries down toward a warmth alien to all its experience. Now it was cold beyond imagination. The intergalactic night had drained away such heat as it had once possessed. Yet there were seas there, seas of the only element that it can exist in the liquid form at a fraction of a degree above absolute zero. In the shallow oceans of helium that bathed the strange world, electric currents, once started, could flow forever with no weakening of power. Here, superconductivity was the normal order of things. Switching processes could take place billions of times a second for millions of years with negligible consumption of energy. It was a computer's paradise. No world could have been more hostile to life or more hospitable to intelligence. And intelligence was there, dwelling in a planet-wide encrustation of crystals and microscopic metal threads. The feeble light of the two contending galaxies, briefly doubled every few centuries by the flicker of a supernova, fell upon a static landscape of sculptured geometrical forms. Nothing moved, for there was no need of movement. In a world where thoughts flashed from one hemisphere to the other at the speed of light, where only information was important, it was a waste of precious energy to transfer bulk matter. As you can see, the Arthur C. Clarke in the story wrote very imaginatively about complex intelligent life arising from just electrical currents in superconductors on what we would deem as an insanely cold, seemingly lifeless planet. He imagined that electrical currents, which were only slowly attenuated due to superconductivity, ultimately led to networks of neuron-like networks capable of intelligence. And he proposed a completely different computational substrate that is different from any kind of carbon-based computation that we know from here on Earth, electrical currents in superconductors. Although this is unlikely to be feasible, it does challenge our imagination and challenges the very notions of life. In this talk, I will argue that more objective principles, coupled with a more rigorous definition of life, rather than only what we see on Earth, would better prepare us for life or lifelike forms that may exist elsewhere in the universe. I'm not suggesting that we completely disregard what we see on Earth, but we just keep an open mind and use an objective criteria for life. One such lifelike system is actually the reaction diffusion system called the Belousov-Zhabotinsky reaction, the BZ reaction. It is actually a real chemical oscillator, and it displays complex properties reminiscent of life. I would just like to show you one particular simulation of this from the NetLogo application. So here is a BZ reaction, and here is NetLogo, which is an agent-based simulation platform. There are two chemical species which are sort of inhibiting each other. And the idea is that as you run this reaction, and as you run this reaction over time, you will see complex emergent phenomenon and interesting properties that have almost lifelike sort of properties. They seem to persist for a long time, at least for the right parameter ranges, they would persist for a long time. They would have structures within them. They would have structures similar to sort of cell membranes. They would interact with each other, and very, very complex forms would indeed emerge from them. I will let this simulation run, and as you can see, there are all kinds of interesting patterns and even standing waves that would come up as we let this simulation run for some time. This suggests that novel non-carbon-based computational substrates may have lifelike properties. There are also systems of oil droplets that exhibit lifelike properties. They are able to replicate and consume energy. And oil droplets also have been engineered to have compartments and can derive propulsive power from an external energy source. We can take this analogy even further. We can, for example, suggest, and this is only a suggestion, stars have an energy source and have compartments. They're constantly consuming energy. They can persist for a long amount of time. And then ultimately at the end of that quote unquote lifespan, some stars undergo supernova. These cause local disturbances in sort of neighboring interstellar clouds. This particular supernova then causes neighboring interstellar clouds to collapse within themselves, which then leads to more star formation. Conceptually, this can be thought of as similar to replication. Similarly, spherical droplets, self-propelled colloids, and motile crystals also move about in remarkably lifelike ways. And again, microscopic beads of artificially engineered materials exhibit swarming behavior under the influence of an electrical field. Taking this analogy even further, there are quantum systems that are capable of transferring information like spin and have remarkably lifelike properties. We can look at weather systems here on Earth, like hurricanes that persist for long periods of time. And then elsewhere in the solar system, there are weather systems like the Great Red Spot on Jupiter that has persisted for a very long time and displays complex behavior. It can sort of merge with other sort of weather systems, and then it can persist for a long time. Indeed, it consumes huge amounts of energy. I argue that an objective definition of life, rather than only what we see on Earth, may perhaps better prepare us for life or lifelike forms that may exist elsewhere in the universe. What might the subjective definition of life include? I suggest, only as a tentative first step, the following few criteria. These are by no means exhaustive. These are completely open to debate, and they're completely falsifiable or verifiable in the true spirit of scientific inquiry. I argue that information processing and information is really at the heart of all these computational lifelike systems. These systems need to process information. This is akin to software in sort of human engineered computers. Information also needs to be stored. This is similar to memory or hardware. And indeed, the physical substrate, that is the hardware, and the role of physical space is also very important. Here on Earth, it takes the form of sort of carbon-based sort of life forms, as hopefully that science fiction story, and hopefully as some of the other systems that I've described. Hopefully that gives you a sense of how there may be other non-carbon based lifelike systems. These systems also need to transfer information across both physical space and time. This information also needs to persist. And by persist, I mean that this system will have a certain lifetime. It will be persistent. It will be robust to sort of perturbations from outside. And that information about the system or information within the system will persist, both in space, so that this physical object, if you will, can persist, as well as time, so that it can even pass on this information to sort of future progeny, if you will. If it can replicate, it can transfer this information across time. This is similar to sort of selection and heredity that we observe in life forms here on Earth. And naturally, I think energy and thermodynamics plays a key role. Energy is required in these systems, and there may indeed be energetic limits on information processing and life. In the Belousov-Zhabotinsky system, there are indeed certain model parameters, and only certain model parameters that lead to persistent wave-like patterns. These patterns may have a selective advantage. That is, these behavioral parameters may become dominant in a population. And this is a form of selection or information transfer, if you will. Some features of information processing should or may emerge faster, and the rate of information processing itself may be faster based on the energy or temperature of the system. There may be an optimal range of energy and temperatures for information processing to be viable. Too cold and molecular motion would cease, although, as we saw in the science fiction story, that may not strictly be the case. Computation may indeed go on even a few degrees above absolute zero. And possibly too hot and critical physical structures that need to sustain information processing may dissociate faster than they would arise. So there may be an optimal range of energy and temperatures for these lifelike systems to be viable, which is perhaps why we see these lifelike systems at sort of the current age of the universe. I think thermodynamics may play an important role in studying the evolution of life and lifelike systems, which is why I've come to this conference. And a worthy goal would be to unify thermodynamics and information processing under a common unified framework. I again propose some tentative first steps towards what this unification may look like. This would take a lot of work from the community. And just as a tentative first step, I propose a taxonomy of these lifelike systems, which would form a continuum of lifelike systems, really. And what I really want to do is break down probably this artificial distinction between life and non-life. And what I suggest is that there is a continuum of these lifelike systems. And some of these systems in this taxonomy would fall anywhere on that spectrum. So for example, oil droplets, convection cells, which are found in fluids, clouds, similar to weather systems, stars like we have talked about. Clay is an important piece in this. I will tell you a bit more in the next few slides about why clay actually has remarkably lifelike properties. Naturally, on this taxonomy would be carbon-based life as we know it. Innovations in sort of human society have sort of a life of their own. They tend to sort of propagate through our society. They have a certain lifespan, and then they die off at some rate. Memes, for example, are quite similar. They tend to spread, in certain cases, rapidly. We don't know why certain memes spread more than others, but they do spread. They have a certain lifespan, and then they do engender other memes which are similar to them. Viruses fall somewhere on this taxonomy. They are sort of between non-life and life, if you will. And if you look at the rich history of sort of artificial life, there are all kinds of interesting systems like Linear, Game of Life, games like the Core War, and definitely computer viruses that fall somewhere along the spectrum. There is also a very interesting example in the seminal book by Eörs Sazathmari, where the author talks about a naturally formed nuclear reactor in Africa that existed many millions of years ago. It's a nuclear reactor that actually formed quite naturally underground and was self-sustaining. The fission reactions within itself were actually self-sustaining, and it sustained itself for a really, really long time. This again probably should fall somewhere along the spectrum of lifelike systems. Taking a concrete example, let us take the example of clay, for example. So clay is actually a crystal that dissolves in water or forms some solution in water. And shown on this diagram on the top panel here. And once it dries, it goes back to its crystalline form. And what Graham Kane Smith actually suggested that clay may have formed one of the first lifelike systems on this planet. And indeed, this system may be sort of capable of selection and replication of a certain primitive form. So replication would be that naturally it's a crystal and there are particular types of lattice defects that may replicate. Clay, as it crystallizes, sticks together. And if a particular form of clay is very sticky, it will stick to, for example, a riverbed, and then will sort of make other sort of clay particles stick to it, and it will grow in size. When clay gets dry, it will get dispersed through wind, and then these imperfections in the clay crystal will be propagated through sort of space and time. And then once these crystals again get into water, these imperfections will again repeat themselves. And there is a sort of self-selection process in there, because only certain forms of clay particles which are sticky will actually propagate, quote unquote, and other particles which are not sticky will not propagate. And then these defects will naturally propagate over time and space. This process is remarkably similar to sort of a rudimentary form of evolution. And Graham Kane Smith, many years back, suggested that perhaps the first genes were actually made of clay and not DNA or RNA, as we know now. But regardless whether that theory is true or not, clay particles do seem to be capable of some primitive form of selection and replication. So selection, quote unquote, we can define it as information transfer along time. That is, some systems that persist, whereas others do not. Maybe there are certain properties or parameters in that system that enable it to persist as opposed to others. Is there selection in stars? There may be. Some stars may supernova and may have an advantage that they sort of create more stars over time. Is there some form of rudimentary selection in clay? Again, it is possible. And our work is really complementary to work suggesting that selection, broadly redefined in this way, can act on all kinds of physical systems, such as stars and even minerals here on Earth. That is, there are some minerals which are that are present in higher abundance on the Earth's crust than others, possibly because they have a certain selective advantage. Self-preservation or persistence is really important in these lifelike systems, and actually can arise quite naturally in some of these systems, like the BZ system. So persistence of information is, I argue, is again a very important criteria in these lifelike systems. And I suggest again that persistence, heritability, natural selection actually lie along a continuum. And I suggest, again, as a first step, that this strict dichotomy and division between life and non-life may need to be revisited. What I have shown you is, I think, the glimpse of a theory that will requires more work from the entire community that's assembled here. This taxonomy, I hope, will be one of the first steps towards that. And the key takeaway really is that we can study all these different lifelike systems and hopefully unify them under a single theory of lifelike systems. The field is really, I think, at a crossroads here. We have enough knowledge about these lifelike systems, and this field is really ripe for integration. The situation is quite similar to in the 1970s, when the Harvard biologist Edward Wilson attempted a synthesis and a unification of biology and sociology. Writing in his seminal book, Sociobiology, he said, "This comparison may seem facile, but it is out of such deliberate oversimplification that the beginnings of a general theory are made. The formulation of a theory of sociobiology constitutes, in my opinion, one of the great manageable problems of biology for the next 20 or 30 years." I suggest that we are at a similar crossroad in studying lifelike systems. And indeed, it is out of these kind of deliberate oversimplifications and these kinds of simple models that a general theory may arise. I'm also quite interested in sort of educating the young audiences and the public about these kinds of ideas. With an educator, I've designed activities for children and college students who can better understand these systems and play around with tools that can be played in a web browser and further build on their understanding. A publication is shown here, published in the Journal of Humanistic Mathematics. I have left a link to the story that I gave you a short excerpt on a few minutes back. Please do read it. I will quickly conclude my talk by telling you the key takeaways. I suggest we think of life as computation on potentially any kind of substrate, and that life and lifelike systems really live on a continuum, and that information storage, transfer, persistence of information, that is heredity and selection, are key parts of this theory, as is an energetic and thermodynamic perspective on this. Another key takeaway is that perhaps our current view of life is very anthropocentric and carbon-centric, and there may be gradations of these lifelike systems like stars, other lifelike systems, planetary lifelike systems like Gaia, etc. Carl Sagan, in his novel Contact, wrote that we are trapped by our time and our culture and our biology. How limited we are, by definition, in imagining fundamentally different creatures or civilizations, and separately evolved on different worlds. They, that is, alien intelligence, would have to be very different from us. We hope these perspectives will challenge us to come up with alternatives to our current viewpoint of life, and may motivate novel ways to search for intelligence elsewhere in the universe. I suggest that we can use art and science fiction, combine it with artificial intelligence to reimagine life as we do not know it. I think AI will play a very important role in sort of shaping our understanding of these lifelike systems. So I invite you to sort of close your eyes if you can. Let us imagine a future far ahead in time. The year is 3000, and mankind has just journeyed to the stars. In a small, cold, lifeless planet, far away from our galaxy, far away in cold interstellar space, stuck between two different galaxies, our starship comes to a stop and sees this particular system, a system of liquid helium that has electrical currents flowing through it, that has lifelike properties. The question that I have for you is the following. Knowing what we know now, would we regard this as life? Thank you so much for your time, and thank you so much for listening.